Hello and welcome to another calculus video. We are looking at L'Hopital's rule today. Right? In the textbook, this is chapter 8.7. In this video, we are going to look at the theorem / the rule. All right, we're going to look at the theorem, L'Hopital's rule, but we are going to do this without proof. I know this is uncommon for what we usually do. There will be a proof of this. This proof is involved, so we are separating it from this video. We'll have a separate instructional video on the proof of L'Hopital's rule. All right, but this video is going to kind of focus on using it. Right? In talking about this theorem, there will be a philosophical discussion about what it is to be a superhero. I'm spelling superhero wrong. Let me get that right. Superhero. All right, we're going to have a discussion on superheroes. And then, after talking about that, we're going to talk about an indeterminate form. Forms with an S. All right, we know some of these. We got 0 divided by 0. We have a plus or minus infinity divided by plus or minus infinity. You've talked about this before, pre-calculus. But there are other forms, and we'll talk about all of those. And last but not least, we will actually spend the majority of this video doing examples, right, and making sense of the theorem in practice. So we will have examples for you here at the end. All right, with that said, let's go ahead and get started. Here is L'Hopital's rule. Take a second to read it to yourself. All right, I'm a slow reader, so I just read it, and I figure if I've read it, then hopefully you've read it. But if you need more time, go ahead and just pause. But let's go ahead and unpack this thing. I'm going to start to unpack this thing by circling here at the bottom what the theorem is actually saying. Then the limit as x approaches c of f over g is equal to the limit as x approaches c of the derivative of f over the derivative of g. All right, that's what the theorem is saying. All right, let's move back up towards the top of this page and kind of unpack the requirements in order to use this rule. Let f and g be functions that are differentiable on an open interval a to b. All right, so we're going to be looking at a point C down here. We're going to be looking at a point C. We're going to be looking at an open interval around this point. It does not need to be differentiable at C itself. It just needs to be differentiable everywhere on that open interval except for at C. All right, so let me draw a little picture. Here's our point C. Here's our point A and B. It doesn't really need to be differentiable at that point, but it does need to be differentiable everywhere on A to B. All right, if it's not differentiable here, we'll just move A a little bit closer. We also need it to be the case that the derivative of g does not equal 0 for all x in AB. Once again, though, except at maybe C itself. All right, we don't really care what's happening at the point C. We care about what's happening locally around the point C. So, if we're going to use this rule, that the limit of a ratio is equal to the limit of the derivatives ratio, very powerful rule, you'll see in a second. We just need these rules to be in effect. Right? There's some more stuff that need to be true. Right? If the limit f over g as x approaches c produces any one of the following indeterminate forms: 0 over 0, infinity over infinity, negative infinity over negative infinity, infinity over negative infinity, negative infinity over infinity. If the ratio produces one of these forms, then we can use this rule. Right? This statement is really important because in the future, later in this video, we are going to be looking at applying L'Hopital's rule to problems, and we're not going to have any of these forms. we're going to need to turn it into one of these forms. So this is key. Right? In order to use L'Hopital's rule, we need to be in one of these 5 indeterminate forms here. Well, I guess only 2, 0 over 0 or some form of infinity over infinity. This is L'Hopital's rule. As you can see, this is quite complicated. That's once again, that's the reason why we're going to put the proof for this in a completely separate video. And today we are focusing on understanding it and applying it. All right, so before we start to use this rule in depth, let's just make sure that it works for something that we already know the answer of. Right, the limit as x approaches 0 of sine x over x. All right, the first thing that we need to consider for this first example is, as we approach 0, do we have an indeterminate form of 0 over 0 or infinity over infinity? Do we have one of these forms? And I believe we do. Sine of x looks like this, right? At sine of 0, we have 0. And then x, of course, looks like this, right? The function f of 0, f of x is equal to 0. F of x is equal to x, sorry. F of 0 does equal 0. Right, so we do have 0 divided by 0 here. According to the theorem, we can apply the rule that the limit of the ratio is going to be equal to the limit of the derivatives ratio. The question we need to answer in this example is this consistent with what we know the answer to already be? So I will give you a moment to try to reflect and remember what the limit as x approaches 0 of sine x over x is. It's a nice geometric proof that you did last year. What is this limit? Right. This limit is equal to 1. As you get closer and closer to 0, we end up getting 1. All right, so I'm just going to write that by applying L'Hopital's rule. The limit as x approaches 0 of sine of x over x is equal to the derivative of sine x is cosine x, and the derivative of x is 1. Right, we have cosine x. I have made a huge error, and I'm actually glad I did so that I can tell you guys not to do this. Right? The limit as x approaches 0 of sine x over x does not equal cosine x over 1. What? But you just apply the rule. No. The limit of sine x over x as x approaches 0 is equal to the limit of cosine x over 1 as x approaches 0. I need this limit. Do not drop that limit. You are writing inaccuracies, and we want to pay attention to the details. Details are very important to us. All right, so, okay, cool. So this is equal to the limit as x approaches 0 of cosine x, and we know what cosine x looks like. Not the best drawing, not terrible. All right, that equals 1, right? This is equal to the limit as x approaches 0. I'm rewriting the previous line, right? And that equals 1. Right? Is that what we remember this to be? Yes. So far, with our sample size of 1, we are consistent with what we know the derivative of sine x over x to be. All right, L'Hopital's rule has provided us with the correct answer with a significant less amount of work than I'm sure Mr. Rose spent on sine x over x. Wouldn't it have been great to know this rule when you did this problem a long time ago? Well, oh well. All right, this is L'Hopital's rule in action. Let's dig deeper. All right, here's a problem for you guys to try. To test out your understanding of L'Hopital's rule on the surface. All right, what's the limit as x approaches 2 of x squared minus 4 over x minus 2? All right, we can, before you begin this problem with L'Hopital's rule, real quick, let's verify the answer using past methods. Limit of x squared minus 4 over x minus 2. This is going to be equal to the limit as x approaches 2 of the factored form. All right, doing a little bit of algebra. Boom, boom. X plus 2. And then using this, we're going to get 4. All right, so using L'Hopital's rule, we should get 4. All right, now, before you begin doing this problem using L'Hopital's rule, I want you to verify that L'Hopital's rule applies. It doesn't apply if you don't get one of those indeterminate forms, and it doesn't apply if you break those requirements that were at the beginning of our theorem. Okay, so, are we differentiable? Is f and g both differentiable? Is it smooth? Around the point 2, not necessarily at 2. All right, if at 2 we have a problem, but are we differentiable around 2? Yep. All right, and the derivative of g of x, that's going to be 1. We're not going to be 0. The derivative is not 0 around 2. And lastly, do we get an indeterminate form? And if I plug in 2, I get 0 over 0. All right, so in a past life, you might have been very mad if you got 0 over 0. But when doing a L'Hopital rule problem, 0 over 0 is your bread and butter. We are good to apply L'Hopital's rule. So go ahead and do so. I am going to in 3, 2, 1. All right, so this limit is equal to the derivative of the limit. Because L'Hopital rule applies, we're going to get 2x, the constant goes away, over 1. And that is equal to just an unnecessary, I guess, simplification here. That 1 can take that out, and then boom, we get 4. Wonderful. These are equal. More smiley faces. This page is just covered in smiley faces. This is great. All right, L'Hopital's rule seems to be working. All right, and there will be a proof of this coming at you later. But right now, we're just verifying that it's valid, and then later on, we'll start to apply it to more difficult, more challenging problems. Okay, well, now that we've done a few problems, let's start to think about why this is valid without doing the mathematical proof. Let's think about it in simpler terms, because we all watch the movies, and we all know lots about superheroes. And you may be asking, how does a superhero relate to L'Hopital's rule? How does a superhero relate to math? Well, that's quite simple. But to do so, we need to talk about the 2 axioms of superheroes. Number 1, all right, you are either, or 1 is either. I mean, you might be a superhero, don't get me wrong, but 1 is either a superhero or a mortal. No one is both. No one is both. Right, that's one of our axioms of superheroes. I mean, just think about it. No one's both. And number 2, if a superhero fights a mortal, the superhero wins. Every time. All right, I know there's some movies out there. I know there's some, humans that have beaten superheroes, but in order to proceed with this analogy, you must understand and accept these 2 axioms of superheroes. A person or a being, 1 is either a superhero or a mortal, but no one is both a superhero and a mortal. And if a superhero fights a mortal, the superhero wins every single time. These are our 2 axioms of superheroes. All right, let's further this analogy by introducing 2 superheroes. Two superheroes that we hold dear in analysis 1B. Infinitus and Captain Zero. We have 2 superheroes, Infinitus and Captain Zero. This is not a course on morality. I'm not saying whether Infinitus or Captain Zero is evil or good. But these are our two superheroes. And they're superheroes. What might you ask? What are their superpowers? Well, their superpowers are the same. Right? They can pose as the other. Right? Their superpowers are one in the same. Right? Captain Zero can appear to be Infinitus, and Infinitus can appear to be Captain Zero. They can pose as the other. Right? You might see Captain Zero, and you might think that it's Captain Zero, but really, you might be looking at a very sly Infinitus. Or, once again, this is not a class of morality. You may be looking at Infinitus, but really, it's Captain Zero. All right, be careful. Their superpower is that they can appear as the other person. Quite a useful superpower if you think about it. If I had the power to appear as Mr. Schwartz, I would have, I don't even know what mischief I'd get up to, but it could be dangerous. Or I could save the world. There's one last thing I need to say, and this might make you think that Infinitus is more powerful, but I urge you to not make that assumption. Right? Infinitus has a dark side. Infinitus has a dark side. Negative infinity. Infinitus has a dark side. Negative infinity. However, Captain Zero does not have a dark side, right? Because negative 0 is the same as 0. Right? Captain Zero has no dark side. All right, once again, this is not a course on morality. I'm not saying that Infinitus is better than Captain Zero, stronger than Captain Zero, vice versa. I'm not saying that Infinitus is good versus evil. I'm not talking about the intentions of these heroes. I'm just saying their powers. All right, they both have the ability to pose as the other. And Infinitus has a dark side. I forgot to write the word side. Infinitus has a dark side. All right, at this point, you might be asking, why am I watching this video? This has nothing to do with math. Well, you would be incredibly mistaken. Take the following problem as an example. The limit as x approaches 0 of x over 4. What is the answer here? All right, well, let's ask ourselves. What happens as I go to 0? Well, the numerator goes to 0 and the denominator stays as a 4. Well, if we move back to our axioms of mathematics, we have a superhero, Captain Zero, fighting a mortal 4. Our axiom number 2 says that when a superhero fights a mortal, the superhero wins every time. This is Captain Zero versus 4, a mortal. No cape. All right, 0 wins. Captain Zero wins. All right, we have infinity. We have infinitus. We have 0. We have Captain Zero. And then we have all these other real numbers. Those are our mortals. And whenever a superhero goes up against the mortal, the superhero wins. That was example number 1. Example number 2. The limit as x goes to 0 of x over 4 times 10 to the 8. That's a 1, 2, 3, 4, 5, 6, 7, 8 zeros. I believe that's 40 million, maybe even 400 million. I think it's 400 million, right? You might think 400 million. That's a big number. That's a strong mortal. Pfft. Captain Zero wins every time. The limit as x goes to 0 of x over 400 million is 0. Captain Zero wins. Or example number 3. That's a circle and a 3 at the same time. That was fun. Example number 3. The limit as x goes to 0 of 4,000. It's a big number. Strong mortal over x. All right, we have 4,000 over 0. Captain 0. Wait. As this goes to 0, that goes to infinity. This is oh my gosh. We have just found an example of infinitus in disguise. Infinitus wins against a mortal. Once again, superheroes always beat mortals. Superheroes always beat mortals. And we have found an example of this superhero using its power. We have 4,000 over 0. We think it's Captain 0. No, it is Infinitus in disguise as Captain 0. At this point, you may be thinking to yourself, these are pretty mean superheroes. Almost like supervillains are fighting all these mortals. Well, what happens when two superheroes clash? Bam! Our analogy continues. It is precisely when we are in indeterminate form. When two superheroes go at it. LHopitals Rule says to look at how the graphs are growing. Look at the rate of change, the derivatives of the functions to determine what is happening. Let's say I have the limit of e to the x over x as x approaches infinity. Let me write that infinity a little bit better. All right, if I, as x goes to infinity, e to the x goes to infinity, x goes to infinity, we have infinity over infinity, right? We have infinitus on the top, and it looks like infinitus, no. 1 over infinity, that's 0. This is Captain 0 in disguise. We have, bam, a fight between superheroes. And we need to apply LHopitals Rule to determine who wins this fight. Because while they are both superheroes, not all superheroes are created equal. Let's apply LHopitals Rule. The derivative of e to the x, well, that's just e to the x. And then the derivative of x, that's just 1. Oh, this is infinity. Right? Infinity over infinity. The numerator, infinitus, is pulling this problem to infinity. Captain 0 here in disguise is pulling it down to 0, but it looks like in this battle, infinitus has won. The essence of LHopitals Rule is how strong is the superhero. Which superhero is growing faster? And in this case, e to the x is certainly growing faster than x. E to the x looks like this. X looks like that. E to the x is certainly more powerful. Infinitus wins in this case 10 times out of 10. If there is a mortal involved, the superhero wins. But when there are superheroes, when there are multiple superheroes involved, we need to inspect. We need to apply LHopitals Rule. Here's another example. The limit as x approaches infinity of e to the x over x cubed. Okay, all right. X cubed grows pretty fast. E to the x grows pretty fast, right? Looking at this on the surface, as x goes to infinity, I'm going to have infinity over infinity. Cool. This is a battle. Bam! This is a battle between superheroes. Let's apply LHopitals Rule. The limit as x approaches infinity of e to the x over 3x squared. As infinity, that's going to be infinity over, oh no, infinity. Bam! Another battle. We must continue. Let's apply LHopitals Rule once again. E to the x over 6x All right, as x goes to infinity, we have infinity over infinity. Bam! We have to apply one more time. The limit as x approaches infinity of the derivatives of these guys. E to the x is pretty darn powerful. It resists change. It's going to be a 6. And then, 6, that's a mortal. E to the x wins every time. Superheroes defeat mortals 100% of the time. That is one of our axioms. The limit as x approaches infinity of e to the x over x cubed is equivalent to all of these. And the final one is one we can evaluate. Infinity. Infinitus wins again. With this problem in mind, let's look at one more. We got a lot more in our pocket here, but let's apply what we just experimented with there. Limited as x goes to infinity of e to the x over x to the 18. What do you think is going to happen here? And what conclusion can we make? All right. So e to the x, that's infinity over infinity. Bam! This is a battle between superheroes. Infinitus versus Captain Zero in disguise. All right, but if I keep doing this, and I do this 18 times, I'm going to realize that e to the x will beat x to the 18th. All right, conclusion. Right? E to the x is more powerful than polynomials. E to the x is mightier than polynomials. Well, what happens when e to the x goes up against another e to the x of the similar form? Let's look at another one. What about like the limit of e to the x over e to the x? Once again, we're going towards infinity. What's happening here? Or who wins here? Can anyone beat infinitus on the top? Well, let's take the derivative. All right, let's apply L'Hopital's rule. Well, let's validate that L'Hopital's rule works here. Infinity over infinity, infinitus over Captain Zero. Bam! This is a battle. Differentiate the numerator and the denominator. We're going to get e to the x over e to the x. So we're going to get e to the x times the derivative of the object inside. That's e to the x. Those are going to cancel. Limit as x goes to infinity of 1 over e to the x. All right, who wins here? Right, we have one immortal. We mortal. And e to the x in the denominator. That's Captain Zero. In disguise as infinitus. Captain Zero is applying his superpower a lot today. All right, as x goes to infinity, we get 0. Captain Zero wins. And with all of that said, this brings me to my final point. When is it that two superheroes fight? 0 over 0. Infinity over infinity. Plus or minus those. But what are the other superheroes? What are the other indeterminate forms? All right, so we're looking for battles. Bam! We're looking for battles between superheroes. So I think it'd be a wise thing to start thinking about other combinations of 0 and infinity. How about 0 divided by infinity? Is that a battle? Is that a battle? And no, it's not. This is not a battle. Right? This is Captain Zero on the top. And this is Captain Zero on the bottom, disguised as infinitus. Captain Zero. On the bottom, this is Captain Zero twice. Right? This is not a battle. Right? And that's the essence of why this superhero analogy is so powerful. When do we apply L'Hopital's rule? We apply L'Hopital's rule when there's indeterminate form. What is indeterminate form? When there's a battle between superheroes. And then Captain Zero might have some internal conflict with himself, but here, both of these are pulling towards Captain Zero. How about infinity over 0? Plus or minus. I'll throw plus or minus over here too. All right, this is infinitus on top. And infinitus on bottom. posing as Captain Zero. All right, 0 in the denominator pulls towards infinity. All right, this is not a battle. We have 0 divided by 0. We have infinity divided by infinity and all of its plus or minuses. We have 2 forms. I claim that there are 7 forms. And I challenge you right now to think about when there is this indecision. When is there a battle? Bam! When is there a conflict? Here's another one to get you to start thinking. 0 times infinity. We have Captain Zero over here pulling towards 0. And we have Infinitus over here pulling towards infinity. There is a battle. Bam! There is a battle. This is our, and there's no particular order, but this is the third of what I claim 7 indeterminate forms where there's a conflict between superheroes. Here's another one, but once again, I do encourage you to think about when these conflicts happen. But what happens if I have infinity to the 0, exponentiation? All right, what's this infinity doing? This infinity is pulling the number to infinity. This is infinitus. The 0, Captain Zero isn't pulling this actually to 0 anymore. Captain Zero has alternate motive. Captain Zero is trying to pull this to anything to the 0 is 1. This isn't Captain Zero. This is One Punch Man. Didn't think there were other superheroes, did you? It's not just 2. It's a whole multiverse of superheroes. There is a battle. There is a urged pull towards a number in indeterminate forms. That is when we have a battle. That is when we need to apply LHopitals Rule, but I'm going to remind you right now that these are the only 2 forms that LHopitals Rule permits. All right, but we can use LHopitals Rule in all these other problems in a very clever way. But let's get all the indeterminate forms first. We got 1, 2, 3, 4. We got 3 more. I claim that there's 7. All right, what other 2 numbers or numbers and ideas might pull towards a specific number? All right, how about, well, if infinity to 0 worked, how about 0 to infinity? Huh. So we have 0 here, and we have infinity here. As I get closer and closer to 0, I raise to infinity. Is infinity pulling me away from 0? Think about this for a second. As I get closer and closer to 0 in the base, and I get closer and closer to infinity in the power, this is not indeterminate form. If I have 1/2 to the 1 million, 1/2 gets smaller and smaller and smaller. Right? The second I pass that threshold of 1, this infinity is not pulling me to infinity. This infinity is pulling me to 0. The 0 is pulling me to 0. This is Captain Zero fighting itself twice. This is, once again, Captain Zero in disguise. Right? This is not indeterminate form. Let's get rid of this garbage. That is Captain Zero trying to confuse you. Well, let's go back to One Punch Man. What about 1 to the infinity? As infinity gets bigger and bigger and bigger and bigger and bigger, well, it kind of depends on what's happening with 1. If I'm a little bit less than 1, something a little bit less than 1 raised to the really massive power, it gets really close to 0. And something just bigger than 1 raised to the infinite power, or a really massive power, it gets massively big. There is a conflict here. Bam! There is a conflict here. All right, what the heck is happening? This could be anything between 0 and infinity. This is absolutely indeterminate form. We have no idea what's going on here. There is a battle in which we need to figure out who is stronger, this 1 or this infinity. This is indeterminate form. We have 0 divided by 0, infinity divided by infinity, 0 times infinity. infinity to the 0, and 1 to the infinity. These are 5 of the 7 indeterminate forms. And just to make this last one a little bit more clear, this is often a useful tactic to help students understand why 1 to the infinity is indeterminate. But I can rewrite 1 as a to the 0, where a is some constant, to the infinity, which is equal to a to the 0 times infinity. Bam! That is indeterminate form number 3. All right, number 5 is just another version of number 3. We got 1, 2, 3, 4, 5. All right, how about these last two? Number 6 and number 7. How about infinity to the infinity? Oh no, that's totally not going to work. Infinity, massive number raised to a massive number, that is getting closer and closer to infinity. This is Infinitus working with himself. All right. Wait, but that's 0 base did something weird. 0, how about 0 to the 0? Because we have this a to the 0 is 1. This is One Punch Man. Down here, 0 to the something power. That's 0. That's Captain 0. All right, this is an indeterminate form. There is a battle here. That 0 power, as I get closer and closer and closer to it, it is dragging this number, 0 to the 0. And remember, these aren't literally 0 to the 0. These are the limits as I approach 0. So as my base gets closer to 0, it's pulling the total number to 0. But as my exponent gets closer and closer to 0, it's pulling the number to 1. This answer could be anywhere between 0 and 1. All right, this is a battle. This is our 6th indeterminate form. 0 over 0, infinity over infinity, 0 times infinity, infinity to the 0, 1 to the infinity, and 0 to the 0. We have one more. We have one more indeterminate form. And this one, I would argue, is the most sneaky of the battles. This battle happens in secret. This is Superman versus Bizarro Superman. This is, I want you to think back to Infinitus's other power. Infinitus has a dark side, negative infinity. Our final indeterminate form is infinity minus infinity. Infinitus battling himself. Internal conflict. This is our final battle. Infinitus versus himself. Think about it. If I have a massive number and I'm subtracting another massive number, I have no idea what that final result is going to be. It could be 0. But if the first infinity is larger than the second infinity, then it might be infinity. If the first infinity is smaller than the second infinity, maybe it's negative infinity. Maybe it's somewhere in between. We have no idea what this is. This is a battle. This is Infinitus versus himself. These are our indeterminate forms. 0 over 0. That's a battle between Infinitus and Captain 0. Infinity over infinity. Yet another battle between Infinitus and Captain 0. 0 times infinity. Captain 0 versus Infinitus. Infinity to the 0. That's Infinitus versus One Punch Man. And then 1 to the infinity, that's One Punch Man versus Infinitus. And then 0 to the 0, that's Captain 0 versus One Punch Man. And infinity minus infinity is Infinitus versus Bizarro Infinitus, Dark Infinitus. A battle with himself. But now that we've been introduced to the indeterminate forms, the battle between superhero and superhero. Once again, this is not a morality class. I do not know if the superheroes are good or bad. Right, but what I do know is that LHopitals Rule is only valid when we have 0 divided by 0 or infinity divided by infinity. So if we are presented with one of these 5, we must somehow turn it into one of the left 2. Sometimes it's easy, sometimes it's difficult. Here's our first example of a problem of the right 5 forms. What is the limit as x approaches infinity of x times sine of 1 over x? All right, first of all, is this a battle? As x goes to infinity, my first term goes to infinity, and my second term, sine 1 over x, sine of 1 over, as x goes to infinity, this gets closer to 0. Sine of 0 is 0. This is 0 times infinity. Bam! This is a battle. All right, so we want to apply L'Hopital's rule, but we need to get it in the form of a ratio. So how are we going to do this? Well, for problems like this, it's kind of simple. And you might have already seen it. I'll give you a second. Pause if you need. Turn this into a ratio. The answer is put that x in the denominator using a reciprocal. That's it. All right. And is this indeterminate form? Or is it Infinitus fighting himself, or Captain Zero fighting himself? Let's find out. As x goes to infinity, the denominator goes to 0. And the numerator, that goes to 0. We are good. Bam! This is a battle. We can use L'Hopital's rule. So let's do it. The numerator is going to be cosine. So do not want to forget this. We're going to have cosine of 1 over x times the derivative of 1 over x. That's just x to the negative 1. Bring down the negative 1, negative 2. There we go. Negative 1 over x squared. That's all going to be all over. We just got that. Negative 1 over x squared. The negatives go away. The x squareds go away. And then this becomes, let me go ahead and erase this scratch work. The limit, as x goes to infinity, of the cosine of 1 over x. And as this goes to infinity, this thing goes to 0. As x goes to infinity, the argument goes to 0. And the cosine of 0 is 1. This 0 is bringing the limit towards 0. This infinity is bringing the limit towards infinity. And where do they settle? Somewhere in between. All right, we settled at 1. The answer to this problem is 1. Here's another example. The limit as x goes to 0 from the positive side, or the right-hand side, of 1 over x minus 1 over the square root of x. Question 1. Is this a battle? Well, 1 over 0, that's going to infinity. And then minus 1 over 0, that's going to infinity. This is a battle. This is Infinitus versus Bizarro Infinitus versus Evil Infinitus. Or I guess Dark Infinitus. I don't want to say that whether an Infinitus is good or evil. But this is indeterminate form. So I need to turn it somehow into 0 over 0 or infinity over infinity in order to use L'Hopital's rule. Take a second to think about how to turn this into L'Hopital's rule. I'm going to do it in 3, 2, 1. All right, I'm going to find a common denominator. I'm going to multiply this by root x over root x. And I'm going to have 1 minus root x. And before I proceed, we must verify that L'Hopital's rule is valid. Do we have a new indeterminate form? We've gone from an indeterminate form, but have we ended up on 0 over 0 or infinity over infinity? Or any combination of plus or minus infinity over plus or minus infinity? Well, if I plug in 0, 1 minus 0 is 1 over infinity. This numerator is immortal. It is not 0. It is not infinity. Right? Superheroes win 100% of the time over mortals. This is as I go towards 0 from the positive side. This is infinity. Infinity wins. Let me just double check my signs. As I come from the positive side, the denominator is positive infinity, and the numerator is going to be positive 1. So this is positive infinity. All right, if I was coming from the negative side, this would have been negative infinity. All right, but this is not a L'Hopital rule problem at all. This is just a simplified problem. Right? We had indeterminate form, but there is no need to apply L'Hopital's rule. All right, this is a mortal versus a superhero. All right, I got one more example for you. Example number 3. And then we'll close out this video with some final remarks. All right, my final problem for you is the limit as x goes to infinity of 1 plus, let me write a 1, 6 over x to the x divided by 2. Let me just make it a little bit more neat. This is our final problem today. All right, I've been doing a lot of these problems. What I want you to do real quick is just first go through the motions of what you must verify in order to apply what we've done today. All right, the first thing is this indeterminate? Well, as x goes to infinity, my base in this exponent, 1 plus 6 over, this is going to 0. So the base is going to 1, okay. And the exponent is going to infinity. This is 1 to the infinity. Is this indeterminate form? Well, as I get closer and closer to 1 in a base, 1 repeatedly is going to maybe be 0, maybe be infinity, I don't know. This is indeterminate form. We do not know who's winning this battle right now. So we need to somehow turn this thing into a L'Hopital rule problem. And that is kind of hard. I'm going to give you guys a chance to pause right here and think about how you can turn this problem into a ratio. My hint to you is we have exponents. And it would be awesome if we didn't have exponents. Why? Because we want this to end up being a ratio between two things. We want to somehow get rid of this exponent. All right. Well, I'm going to do something clever real quick, and maybe you'll know what to do once I do this. But the limit of this thing, I'm going to turn this into an equation. The limit as x approaches infinity of y is equal to the limit as x approaches infinity of this thing. 1 plus 6 divided by x over x divided by 2. How does this help us? I have an equation here. I'm going to take the natural log of both sides. All right, why would I want to do that? Well, the natural log has the ability to bring powers down. Then I can do the reciprocal thing and then turn this into a ratio. Right? Can I bring the natural log into the limit? Well, the natural log is a continuous function. So it's not going to be affecting the differentiability, the limit of our problem. So I'm going to go ahead and do that. And then at the end, I'm going to deal with this natural log of y. But I'm bringing the natural log into my limit. And then I'm going to use my log rules. I'm going to take this. I'm going to take this to the next page. And I'm just going to go ahead and get rid of that. I don't want that. Come on, eraser. There we go. All right. I now have the ability to bring down that x divided by 2, the limit as x approaches infinity of x divided by 2 times the natural log of 1 plus 6 over x. Not to the x squared, I brought it down. All right, I am moments away from being able to apply the rule. All right, so if I go ahead and I bring that to the bottom, the L'Hopital's rule. All right, can I apply it though? Do I have indeterminate form here, or is my answer given to me? Let me add this while you think about it. All right, if I plug in infinity, I'm going to get ln of 1, that's 0. And down here, 2 over, as I go to infinity, that's getting closer and closer to 0. I have, bam! This is indeterminate form. I can apply L'Hopital's rule. So let's go ahead and do that. the derivative of this is going to be 1 over 1 plus 6 over x times the derivative of what's inside. That's going to be negative 6 x to the negative 2 all over the derivative of this. That's going to be negative 2 to the negative x to the negative 2. I believe I'm right. Let me just check. Yep, that is correct. And these cancel. These cancel. That becomes a 3, and I have 3 over 1 plus 6 divided by x. I am forgetting some major mathematical notation. These are not equal. I hope that you guys at home are freaking out. I need my limits. All right, and this is all not y, but ln y. That's going to be very important in a second. Right, and as x goes to infinity, 6 over x, that goes to 0, and we have 3 over 1, that is 3. All right, we are done. Psych, we are not done. We are not done. I repeat, we are not done. We have the limit of ln y as x goes to infinity is equal to 3. That is not what we want. Let me take you to this next page. We have just verified that the limit of the natural log of y, we want y. The limit of the natural log of y as x goes to infinity is equal to 3. We have to do one final step, and that is the best step in the world. It is to e it up. All right, if we e this up, we get e to the 3. And then that e gets pulled inside the limit. We have e to the ln y. Those things disappear together. And we have the limit of the original problem is e to the 3. This final step right here is the number one step that students forget. Do not forget to e it up. I repeat, do not forget to e it up. The last thing that I will say is that you will use this natural log method. Step 1, take the natural log. Step 2, turn into multiplication. Step 3, turn into quotient. Step 4, apply L'Hopital. And then step 5, solve ln y / e it up. All right, you will use these 5 steps in the following forms. Infinity to the 0, 0 to the 0, and 1 to the infinity. All right, you will use this obnoxious method. I wouldn't say it's obnoxious. You will use this creative method with these following 3 forms. All right, and that's it. L'Hopital's Rule, section 8.7. Read it for some extra information. Well, I wouldn't say extra information. Read it for some reiteration of the information. I think it'll be useful to you. I think it'll help you in the long run. But we looked at the theorem today. We did not do a proof. We broke the cardinal rule of math. But a proof will be coming soon. Right? We talked about superheroes and why superheroes relate to math. All right, that led us into the indeterminate forms, 0 over 0, infinity over infinity, etc. We had 7 forms. I recommend just knowing them. All right, but we in doing so, we talked about why they are indeterminate forms. There is a battle between superheroes. And then throughout this entire lesson, we did a ton of examples, with that final one being the most complicated of them, but nothing that you cannot handle. With all of this said, I'm going to close this video out here. But once again, if you have any questions, bring them to class. We will do some problems together. And I'll leave you with one final